Alright, so I'm starting at the bottom of page 137 of the revised notes. So if you want to follow along, which you should. Um, so I wanted to start with our RBF, the radial basis function, and how to train it. So just as kind of a step-by-step how to train or training the RBF. Okay, so what do we need to have? We assume we have P points and Rn as our input. So that's usually in the matrix X. Also, we'll assume we have P points and Rm as our output. And those are targets, so I usually call them T. And then we also have K centers. And how did we get those K centers? Well, for this part, we're going to assume that we've got them through clustering. That's popular. Another way to do it is through random center selection or random selection of data points. So we just choose K points of input at random. And there are other ways of getting it, because what I want to focus on in this section is how to actually solve or set up and solve the RBF equation, using linear algebra. Okay, and so what is exactly the problem that we're trying to solve here? So step one, form the distance matrix. Between the K centers and the P data points. Actually, it's not going to really be P points, right? Because normally we would be running this on a training set. So there'll be we'll just assume that there's P points in the training set. Okay, now what size is the distance matrix that comes out? Because it's really critical on these to keep track of the dimensions. So the dimensions of the distance matrix is, can you read that? Okay, let me go back to white again. K by P. Okay, and so again, these are distances. And so if D is our distance matrix, then Dij is the distance between which 2 points? The ith center, because the I is running from 1 to K, and the jth data point, because J is running from 1 to P. Good. All right. Now, what am I going to do with the matrix D? That's K by P. Step 2. We're going to form the design matrix, what's called the design matrix phi. Oops, geez, I'm so used to typing this on LaTeX. Phi, capital Phi has little bars on the top and bottom there. And the matrix phi is found by taking phi, little phi, let me write it this way. Phi ij is equal to phi of ci minus xj. Oops. Right, and using a Gaussian, right, that would be e to the minus our spread variable. I don't want to use sigma, that's our standard variation. So maybe minus b times, that looks like a convolution, times our ci minus xj squared, the norm squared. Okay, good. So this is only with the exponential function, right? And I'm thinking of b as being the spread, and the spread we talked about in the last video, I think. MATLAB's estimate is b equals, let's see, minus, or the square root of minus the natural log of 0.5 divided by whatever spread constant you want. I have to sigh a little bit because I don't know why they would leave it as minus natural log of 0.5. Why would you do that? Right? Because that's equal to the natural log of 2. Right? I'll let you prove that. Okay. So I don't know why MATLAB did that. Okay. So anyway, we have our design matrix now, capital Phi, and capital Phi is what size? It's the same size as the distance matrix, so that is k by p. Good. Step 3. We're going to form our equation now. Form the affine map, if you will. You don't have to. You could skip this step if you want, but it's good to be sure what you're doing. So we're going to take our weight matrix W times our design matrix Phi. We're going to add in our bias terms B. Now remember, this is not linear algebra notation, because in linear algebra you cannot add a vector to a matrix. And so this is going to be equal to our target values T. Good. So let's do our count again. This is k by p. This is m by 1. This is m by p. And this is, did everybody say m by k? Good. All right. Now, how do I convert the affine map to a linear map? Do you remember how we did that? Well, we rewrite the left-hand side so that W hat is equal to the augmented matrix WB. Sometimes I leave the bar off, sometimes I leave it in there. And then capital Phi is actually going to be Phi, but then we augment it by a row of zeros. Oh, Phi hat is the matrix Phi with a row of zeros down at the bottom. So again, think about what sizes things are. This is now m by k plus 1, right? Because we added a column onto the end. And this is now k plus 1 because I added a row on the bottom times p. Good. And so now we're solving w hat phi hat equals t for w hat. Okay, how do we do that? Did you say take the pseudo inverse? Phi hat, right. So now we take, let phi hat with a dagger or a cross or a plus. I guess some people use a plus. It's easier to, yeah, otherwise it can look funny. Okay, let this be the pseudo inverse of phi hat. And remember that the pseudo inverse is computed using the SVD. So that's just a little review. And the reason this is nice, right, is because if you take phi hat and then break it apart into its components, right, what you can do is you can inspect the singular values to see how close to 0 your singular values get. Right? And so now remember, this is going to be a wide matrix, phi hat. Phi hat is a wide matrix. And so we're hoping that phi hat is actually going to be full rank, but it may not be. And so you can see how close to 0 they get. And so um, if you use the pseudo inverse command, there's a built-in value of the singular value, right? Or a built-in tolerance. So built-in, or ready-made, I should say, ready-made software for the pseudo inverse takes a guess at what the cutoff should be, or the tolerance. And sometimes it can be a bad guess because they're usually pretty conservative, so they're going to be like very small numbers. But you may want to say, well, I've got a lot of noise in the data, or the data is not very sure, so I may want to increase that tolerance level a little bit, and cut off the stuff that I know is going to create problems when I try to do the inversion. Okay, so we talked about this kind of stuff before, but I just wanted to emphasize that that is in here. Although for this current homework, you can go ahead and just take the pseudo inverse command. That's PINV. That's both in MATLAB and Python. And that will do it. Okay, so what's the last step here? I've only got I already went over time, but let me go ahead and finish our equation. So step 6 is that W hat is equal to T times phi hat dagger. Good. Now, again, think about sizes. So T is going to be M by P. And so this is phi hat was K plus 1 by P. And so when we formulate the inverse, remember we're transposing everything. And so this is going to be P by K plus 1. And so therefore we see that M, or W hat, is M times K plus 1. Good. And so you can either leave your answer as W hat, or you could say that W is equal to, the first K columns. And then you could take B to be the last column, if you want to. If you don't want to, then you can just leave your answer as W hat, but then you have to construct phi hat instead of using phi when you do your design matrix. All right, so we're going to talk about that in the next video. I've already gone way over. I'll see you in the next video.